So this will be a short lecture this morning on hydraulic resistances in microfluidics. In the previous lecture, what we looked at was a general expression for the pressure drop in shapes of arbitrary channel or arbitrary cross section. And as part of that, one of the things that we were able to derive was this expression here, which gives us a calculation for the hydrodynamic entrance length. And that's the region where the flow is developing. One of the features of microfluidics is because the Reynolds number is so small, typically very much less than 1, or if you had a Reynolds number of 10, it would be quite large in a microfluidic system. You end up with these very short entrance lengths, and sometimes you can actually neglect the entrance region and just treat it as if it's fully developed. So in a lot of cases, your flow will develop very, very rapidly. Now, it's always important just to check it out, and if you can use if you can neglect the hydrodynamic entrance length, then your calculations become a lot more straightforward. So if we consider that you can neglect the entrance region, so you're just dealing with a region where the pressure drop is linear with flow rate. So that's in the fully developed region. What we can do is we can use this analogy here, and it's an analogy, with Ohm's law. So V equals R times I that you'd remember from first year electrical engineering. Okay, so in fluids, the pressure drop up here corresponds to the voltage. The flow then Q corresponds to the current. Okay, so we have the pressure drop is equal to a resistance times the current, and that's purely because it's linear with pressure drop. Okay, this does not work in the entrance region where you have nonlinear effects. Okay, so you have pressure balanced there with inertia, whereas in the fully developed region, we have pressure balanced with friction. So we have this requirement of a constant pressure drop, because if the flow isn't, if the pressure isn't dropping in a constant manner, then it must be accelerating. Okay, and in the inertia region, the entrance region, it is accelerating. Okay, as you move along the streamline, the flow is changing the velocity is changing its magnitude. Okay, so this really only works in the fully developed region. So if we develop that, based on our expressions for fully developed flow, we can calculate an equivalent resistance. And what that does is, it's done here, this is taken from Bruce's excellent book, in Theoretical Microfluidics. What we have are a series of calculations based on the solution. So if we look at, for example, the parallel plate one here. Okay, so we can see that this is the equivalent expression for the hydrodynamic resistance. And we have the rectangular square one here, and then we have the rectangular one. Okay, and you can see, based on the expressions that we derived earlier, also for this one here, you can derive what the hydraulic resistance is. So the terms hydraulic resistance, hydrodynamic resistance, flow resistance are used. If we have an arbitrary shape, you can use this kind of approach where it's 2 mu L E squared over A cubed. Okay, so perimeter squared and area cubed. Now, one thing to notice in all these expressions is that we only have viscosity. Note here that is using the symbol eta. I think it's eta anyway. My Greek isn't very good. Eta for viscosity, whereas we tend to use mu traditionally. Okay, and that's just a European thing. So mainland Europe, they tend to use eta sometimes, or mathematicians tend to use it. So anyway, just always include the nomenclature and stuff, and check the nomenclature to be clear from that. So we can see that there's always just a viscosity present, there's never a density present. And again, that's because the physics of this is dominated by viscosity. So it's a pressure viscous balance is what you're dealing with. So you don't have any density terms inside there. So there's no Reynolds numbers in this. And we discussed that before in class in one of the tutorials. In Bruce's book, he does a very nice thing where he takes an example and calculates some values. And again, that's important for engineers because we like numbers. We like to see how big things are and look at things in relation to each other. And the first point is that, okay, it's 10 to 11 here. So these are big numbers. So resistances are high in microfluidic systems. And it's quite useful here to compare this one with this one and with this one. Okay, so H here is 100 microns and W is 300. So what we have here is 100 micron square channel, so a typical size feature that we'd have in a microfluidic system. And we can see that we've got a resistance of 2.4 by 10 to the 11 gigajigs Pascal seconds per meter cubed. And if we increase that in size, so we make it a rectangular channel and it's 3 times wider. So now H is changed to W, so W is 300 microns. We see that there's a substantial decrease in the resistance from 2.84 to 0.51. Okay, so there's quite a lot of bang for your buck in opening up the size of the channels. And then if we compare these two, here the two plates, the parallel plates and the rectangle, we can see our expression that we had earlier, minus 1 minus 0.63 H over W, and that is the parallel plate solution, which you should be able to easily work out by hand yourself. And we see that there's a 20% difference there in those two. Okay, so the effect of the sidewalls is still manifest here at this aspect ratio of a height of 100 and a width of 300. Now, if we have channels in series and they may be different size, so this is a typical thing we do, we'd have connections and fittings between them. We know that in reality, there's going to be a reorganization of the flow in this region here where they're joined together. So the streamlines expand out, and therefore we have an acceleration taking place. So this is an inertial region that I've highlighted there. Now, if that region is small, the contribution of that region to the overall pressure drop will be small. And that's very often the case with microfluidic systems, especially where we have quite long channels. So therefore, we would neglect this and assume that the pressure drop is dominated by the linear portion here and the linear portion there. And this means then that we can just add the two of them together. Okay, so we calculate the resistance for the first tube, and we simply add it on to the resistance for the second tube or channel. Right, so it's direct application of Ohm's law. So it's the electrical analogy that you would have used in first year electrical engineering. The other scenario we have, and it's more typical, is that we'd have channels in parallel. So again, this is a typical way in microfluidic systems of getting increasing your yield. So you would put an awful lot of channels in parallel and multiplex your system. And then what you have is a manifolding issue where you're trying to distribute flow down evenly down each of the channels. So getting good balance between your resistances becomes very important. So making sure they're the same length, and the dimensions, the cross-sectional dimensions have very tight tolerances will ensure that you have a good distribution of flow. Now, manifolding of microfluidic channels is a big issue. It's not so big when you have 10 or 20 channels. It's a big challenge when you got 1,000. And there's a lot of work to be done in terms of making sure that the flow resistance from your inlet port to the first channel and all the way to the 1,000 or 10,000 channel is equal. So getting that manifolding becomes more of a challenge. If we take the same assumptions that, again, our entrance regions and are pretty much a very, very small overall contribution to the total pressure drop, and also that our pressure is uniform along here. And again, when you're manifolding many channels, that's not necessarily the case. So we assume that we have a linear pressure drop, or sorry, a constant pressure line along here, a constant pressure line along there. So again, a constant voltage driving the flow through it. We can sum these resistances in parallel. So we end up with this expression here. And if we've channels being identical, then it is simply 1 over n times R1. So the resistance is divided by the number of channels. So again, there's a way of increasing your flow because you're sending the same flow down each channel, so the effective resistance is reduced. Now, these kind of calculations, although they're very simple, they're very useful in terms of doing design work and doing preliminary sizing of your channels. Because when you go to CFD, you're doing a lot of number crunching, and it's not cheap to do CFD solutions. So very often you can get a decent answer just by setting up an Excel and just running some hand calculations to get a feel for things. Okay, so that's a short enough lecture. I hope it's been clear enough. And we'll push on next. We're going to look at the effective compressibility, and this will be a more detailed lecture that will follow. Okay, thank you for listening, and talk to you again soon. Bye-bye.